Today we'll talk about the solution to the Dirac equation. We will give a simple solution for the free particle, so general solution for the free particle. But first, we will give a better form of the Dirac equation, which we call a covariant form of the Dirac equation. So first we start by Dirac equation, which is I alpha x partial of c partial of x plus I alpha y partial of c partial of y plus I alpha z partial of c partial of z plus I beta partial of c partial of t minus beta mc equals to 0. So this is the Dirac equation. So we can multiply both sides by beta, because we know that beta, alpha z, alpha y, and alpha x are matrices. So we can write I beta alpha x partial of c partial of x plus I beta alpha y partial of c partial of y plus I beta alpha z partial of c partial of z plus I beta squared partial of c partial of t minus, oh sorry, we don't have here a beta, so here would be only beta minus beta squared mc equal to 0. So now we write gamma 0 equals to beta. So we set gamma 0 equals to beta, gamma 1 equals to beta alpha x, gamma 2 equals to beta alpha y, and gamma 3 equals to beta alpha z. Now we can write the Dirac equation as I gamma 0 partial of c partial of t plus I gamma 1 partial of c partial of x plus I gamma 2 partial of c partial of y plus I gamma 3 partial of c partial of z minus mc equals to 0. So because b squared is 1, the identity. So we have to keep in mind that gamma 2 is not gamma squared. It is these are indices. So we can write the gamma matrices as gamma mu equals to gamma 0, gamma 1, gamma 2, gamma 3. And we can write also the gamma mu, which is covariant fourth derivative which is partial of mu 0, partial of 1, partial of 2, partial of 3, which is partial of t, or so partial of t would be partial of t, and partial of I would be partial of xi. So we have partial of x, partial of y, partial of z. Now if we replace this equation here, these not equation but these settings that we put, and these here into the Dirac equation, so we can get a better form, which we write as I gamma mu c partial of mu minus m psi equals to 0. So this is the Dirac equation in its full form, and we can see that mu is the repeated index here, which means that we sum over the mu. Now we need to find a solution. First, we will try to find a solution for a particle at rest. So we have the wave equation, the plane wave equation, which is given by this form, px minus at. So this is a free particle plane wave equation, or wave solution, and U is a 4-component Dirac spinner. So this is 4-component Dirac spinner. So we can just write here 4-component Dirac spinner. Now we have the equation I gamma mu partial of mu minus m psi equal to 0. And now this would be I gamma 0 mu 0 plus I gamma 1 mu 1. So we can have here, here is 0 psi, and here psi, plus I gamma 2 partial of 2 psi, plus I gamma 3 partial of 3 psi, minus m psi equals to 0. And now when you try to find partial of 0 psi, this means that the derivative in time of the psi, which is minus I e psi. So you can try. So you have to find the derivative of the exponential, which I think it is pretty easy. So in the similar way, you find the partial of 1 psi, which is I px, partial of 2 psi, which is I py, and partial of 3 psi, which is I pz. Now you plug into the equation, and then you can find that gamma 0 e minus gamma 1 px minus gamma 2 py minus gamma 3 pz minus m times u of e and p times e to the I px minus e times t is equal to 0. In order for this equation to be 0, we need that this part here, this part needs to be 0. So then we can contract these in a shorter form. So we can write gamma mu p mu minus m times u equals to 0. So u is a 4-component Dirac spinner. Now we can continue with particle at rest. So we have E where P is equal to 0 in all of the forms. So we don't have any movements here. So the plane wave equation would be U of E0 e to the minus I e times t, because the p components are all 0. The particle is not moving in any direction. Now, so you in this equation here, you don't have pz, you don't have py, you don't have px. So what you have is gamma 0 e minus m times u. So you have gamma 0 e minus m times u equal to 0, or gamma 0 e u minus m equal to m u. So this is the equation that we have to solve. But first we have to remind ourselves that gamma 0 is 1 0 0 0 0 1 0 0 0 0 minus 1 0 0 0 minus 0 minus 1. Basically gamma 0 would be identity 0 0 minus identity. Now, so we can write and also for u we can write as a 4-component Dirac spinor: phi 1, phi 2, 3 and 4. So now we have E, the energy, times this matrix here, 1 0 0 0 0 1 0 0 0 0 0 0 minus 1 0 0 minus 1 times phi 1 2 3 4 equals to m phi 1 2 3 and 4. If you multiply these two, so this is the just matrix multiplication, then you can find phi 1 phi 2 minus phi 3 and minus phi 4, which is equal to the right hand side part. Now the gamma 0 is diagonal matrix, so since it is diagonal matrix, and here we can have 4 solutions, 4 orthogonal solutions. The first 2 solutions, so we'll write as u1 of e and 0 would be the normalization constant 1 0 0 0, and u2 e0 would be n 0 1 0 0. These 2 solutions correspond to the positive energy solutions. So these are positive energy solutions, E equals plus m. And then we can have the negative energy solutions, E0, which is 0 0 1 0, and U4, which is 0 0 0 1. So we can make an arrow, and these are negative energy solutions. So energy solutions. to energy being minus m. Now we have 4 plane wave solutions, psi1, psi1, n, 1, 0, 0, 0, and now we have e, so we have e to the minus, where is the equation for e to the minus iet. Now for the 2 of the first solutions we have plus m, which in this case is minus imt, and psi2, which is n, 0, 1, 0, 0, e to the minus imt. And then we have psi4 for the negative solutions, 0, 0, 1, 0, e to the plus imt, and so sorry, this could be psi3, this could be psi4, and this 0, 0, 0, 1, e to the plus imt. So these are the free particle solutions for no momentum, so we don't have any momentum or particle at rest, as we can say. Now we can find a general solution. Free particle solution. So we have the Dirac equation as before, e gamma 0 minus px gamma 1 minus py gamma 2 minus pz gamma 3 minus m times u equal to 0. And now we can write this equation in Dirac-Pauli representation, where we write gamma 1s as in Pauli representation. So this can be written as so gamma 0 is I 0 0 minus I times the energy minus 0 sigma times p minus sigma times p 0 minus m, and we can write the identity matrix here, u equals to 0. So this is the Dirac-Pauli representation of the Dirac equation. We have seen before that we can write gamma matrices in the Pauli representation. So now we just need to find this sigma times p. So sigma times p is equal to, so sigma x px plus sigma y py plus sigma z pz, and this would be pz, px minus I py, px plus I py minus pz. So if you plug in this matrix into this part and this part, so you have 4 by 4 matrix, and this identity matrix is 2 by 2, so this would be 4 by 4, this would be 4 by 4, and this would be 4 by 4. So you come back here to this equation where gamma 3, 2, 1, and 0 are 4 by 4 matrices. Now, since we represented 4 by 4 matrices in 2 by 2 form, we know that the spinor U is 4 component. But we can write U as a 2 component, like 2A and 2B, where UA have 2 slots, so it's, and UB has 2 slots. So you have here 2, 1, 2, 1, which makes 4, which makes the 4 component spinner. Now you need to arrange this this equation here. So basically you just need to subtract matrices, and then you can find a form. You can find a form like E minus M times the identity minus sigma times P, sigma times P minus E plus M times E, and the spinner U can be written as UA and UB. Now when you solve this equation, you find the solutions, which are UA would be sigma times P, E minus M times UB, and UB would be sigma times P, E plus M, UA. Now, so we have these 2 solutions. Now to find the solution for the free particle, we need to choose an orthogonal basis, because these states live in the Hilbert space, and we know that the Hilbert state has some bases that might be they are orthogonal to each other. So the simplest one would be to take UA 1, 0 and UA 0, 1. So these are 2 bases that are orthogonal to each other, so 90 degrees. Now let's start by UB. You have UB would be sigma times P, E plus M, UA 1 over E plus M, sigma times P. We know that sigma times P is PZ, Px minus I Py, Px minus plus I Py minus Pz times, for this basis, so we can take 1, 0. You find that UB is equal to let's say 1 over E plus M, and now you multiply these two. Px times 1 is Pz times 1 is Pz, and this part is 0. Px plus Ipy times 1, Px plus Ipy. Now, so the 4 component solution, so the 4 component solution would be U1 of E and P, N1 normalization constant, and then you have here UA and UB. For UA, we have taken 1 and 0, but so here you have E plus M. And for UB, we have PZ, and then we have Px plus I Py. This is the first solution. So this is the first solution. The second solution would be to take UB 1 over E plus M, PZ, Px minus I Py, px plus I py minus pz times 0, 1, where you find that 1 over e plus m is px minus I py and minus pz. So the second solution would be 2u2 e of p n2 over e plus m 0, 1 px, so px minus I py and minus pz. So this is the second solution. Now you can choose a basis for ub being 1, 0 and ub being 0, 1. Then you still have two solutions. So you have u3 and u4, where u3 of e of p would be n3 e minus m in this case, pz px plus I py, you have 1, 0, and u4 you have e p and 4 e minus m, you have px minus I py minus pz 0, 1, like this. Like this. So you have four solutions. u1 and u2, so u1 and u2 u1 and u2 can be identified, so can be identified as the positive energy spinors. So positive energy spinors with E being plus p squared plus m squared, and u3 and u4 negative energy spinors with E being minus p squared plus m squared. So these are the four solutions to the free particle equation, to the free particle Dirac equation. Now what you need to do, you can try also to find the solutions. So these are the solutions for the particles, but what about antiparticles? For antiparticles, so they have the negative, the negative energy. So for antiparticles, the negative energy particle spinors, for example, so negative energy particle spinors, so u3 and u4 are negative energy particle spinors. These are spinors. So u3 and u4 can be written as the physical positive energy antiparticle spinors. So basically, antiparticle spinors are the negative of this negative energy spinors. So what you can so what does this mean? That it is mu1. Before we wrote u1, now we write mu1 for antiparticles, E and P, e to the I px minus E. Energy would be U4 minus E minus P, the exponent in the power of E minus Px minus or plus Et, the energy, and mu to EP exponent, sorry, this is Px minus Et would be mu3 minus E minus P e to the I minus Px plus Et. So for antiparticles, the negative energy particle spinors. So for antiparticles, these are the negative energy particle spinors. So for antiparticles, we take these negative energy spinors and we change the sign, and then we have the spinors for antiparticles. So you can try to solve the equation by yourself, and the end what you should get is gamma mu p mu plus m times mu equals to 0. Before, for particles here we had the minus sign, but for antiparticles here we have the minus sign. So you can try to find the solution. So you have four solutions. So you have mu1, mu2, mu3, and mu4. These spinors, so mu1, mu2, and these mu1, mu2 are very important for building Feynman diagrams, basically. So once you see the Feynman diagram, you can build the equation with the help of spinors. So yeah, for today this is all. Thank you for watching, and we see you next time.